so in the story where Liping led off, Liping started with sort of the very most fundamental aspects and talking about doing calculations and modeling, including quantum mechanics or molecular mechanics. And so where he left us off was with the dream of simulating molecular dynamics, which is basically to build a force field and to simulate what's going on. So actually this is a slide from Michael Levitt's paper in Nature Structural Biology in 2001. If you haven't looked at the paper, it's not that long, and actually it's a nice summary of the history of the field. And one nice thing about this dream, I think, was recently realized in the 2013 Nobel Prize, which was awarded to Michael Levitt, but also with Martin Karplus and Arya Warshel. And so that's been really something that people have been hoping for decades to use molecular dynamics to be able to tackle these types of challenges. But as Liping alluded to, there is a sort of a nightmare that we have to deal with still, and this is the nightmare of long timescales. And basically the issue is that typically nanoseconds are easy, and now with GPUs, maybe hundreds of nanoseconds are easy. But hundreds of nanoseconds still doesn't get us to timescales that we often want, which might be tens of microseconds, 100 microseconds, milliseconds, and onward. And one of the things that we'll talk a little bit about here and later on is how we can use techniques like MSMs combined with OpenMM to be able to get to these long timescales. So in my lab, what we've done is we've tried to put these different techniques together. And so we've been running the Folding at Home Distributed Computing project now for a while. Actually, we're now up to about 40 petaflops, largely due to having a lot of GPUs. And so while not all groups have access to folding at home, actually it's not that hard to imagine having a GPU cluster of maybe 50 GPUs or 100 GPUs. And especially resources like Blue Waters, which is an NSF supercomputer center, or Titan at Oak Ridge National Lab, which is a DOE supercomputer center, you can easily get access to hundreds to thousands of GPUs at these places. And so while not everyone has folding at home, actually these techniques are now, I think, pretty broadly applicable due to the existence of these resources. Okay, but then here's the challenge. The challenge is that what you think you might want is one really fast computer, but instead we have many computers, like many GPUs. And this is where the MSM builder and MSM approach comes in. And I'll give an introduction to it today, right now, but then actually you'll hear a lot more about it later this afternoon. So in the evolution of OpenMM, one of the newest things that we've been pushing to is for OpenMM to be not just a single code and not really just a library, but to be a suite of applications. And the suite includes now many applications, including the OpenMM application itself, but also contributions from other labs, such as Yank, which is a software for doing free energy calculations from John Codera's lab, Force Balance from my lab, and in time we have new projects for refinement of structural ensembles, a code called Odin, which TJ Lane in my lab is working on. And then finally, also as I mentioned, and as you'll hear about later, MSM tools are starting to become quite mature, and we have different tools for running calculations like MSM Accelerator, for analyzing calculations like MSM Builder, and for visualizing. Okay, so let me give you a quick introduction to OpenMM, which is the heart of all these things. So the nature for OpenMM and what we've been wanting to do is something that allows for rapid development and rapid execution. And even if you're not a developer, where you're going to be maybe doing a radically new MD code, often what you might want to do is just something that is not super vanilla. Like you might want to not just run MD, but maybe have some umbrella constraint or have some other minor change. And OpenMM is set up such that those types of things are very easy to do. So the history of OpenMM is actually interesting. It goes back quite a while now. It actually goes back way before the days of people running on GPUs, before CUDA and OpenCL and other GPU languages existed. So actually in 2005, there was a collaboration between my lab and Pat Hanrahan's lab that led to the first MD code for GPUs. And this was written largely by Vishal Vaidyanathan, who was a grad student in my lab, and Ian Buck, who was a grad student in Pat's lab. Actually, if the name Ian Buck sounds familiar, it's because he's actually become quite famous. He, after graduating, left Stanford to go to NVIDIA, and he's the main architect behind CUDA. So actually, when Ian left, we continued to work with people in Pat's lab, especially Mike Houston. And actually, as Mike graduated, he left to go to ATI AMD. And as time has gone on, the original code that they wrote, which was integrated into folding at home, was something that we took out and turned into OpenMM. And the idea is that we wanted to share this code with a lot of people, but also in having an OpenMM as a monolithic application, it was hard for us to turn it into other tools that we needed. And so having it as a library was very powerful. And so more recently, Peter Eastman and Mark Friedrichs were here, and working with people like Scott Legrand and then NVIDIA and others, we got quite a fast platform for NVIDIA GPUs and AMD GPUs. In 2012, I think things start to really quite mature with OpenMM 4.0, 5.0 being released last year, and 6.0 being released just recently. If you look at benchmarks, we're doing really quite well. If you look at, let's say, the speed of running OpenMM on the standard joint Amber Charm DHFR benchmark, the so-called JAC benchmark, typically, the types of timescales that we could hope to get are in the 100 nanosecond timescale, and with various tricks, pushing it into hundreds of nanoseconds per day. But in the end, as I mentioned, 100 nanoseconds per day is really great, and other codes are really pushing to have long timescales here as well. But really, this is sort of just the beginning, because we want microseconds or milliseconds. And so this is running on one GPU isn't going to be enough. To give you some sense of where we're going, we're constantly continuing to add new features. I don't want to go through all of this right here, but actually one of the things that I would encourage you to do is that if you do have features that you'd like to see, you should please let us know. We have our own sense and vision for where we'd like to take things, but we often look to the community for ideas for what would be important new directions. So one other aspect of OpenMM that's important is that its license is very flexible. It has a joint BSD and LGPL license, and without getting into the technicalities of how licenses work, the basic idea of these licenses is that they're extremely permissive licenses. You could take our code and put it in your software, and that's fine. You could even take our code and put it in commercial software, and that's fine. The one caveat, and this is what LGPL does, is that if you take our software and modify it, we'd like to get your, and the license binds you to give the modifications back to us, but that's it. Also, as all academics you can imagine, we'd also be very happy for you to cite us when you use the software. Okay, so with this, we can get to hundreds of nanoseconds a day on a single GPU, and that's actually very impressive, especially comparing, like, when I started here at Stanford, a nanosecond a day was really a big deal. But really, that's not going to get us there. And what we really want to do is we want to get to much longer timescales, much more experimentally relevant timescales. And so how are we going to do that? How are we going to get to these long timescales? And this is where Markov state models come in. And to give you a sense of things, what I want to do is maybe compare two approaches that you may have heard of. So one is the Anton supercomputer approach. And where the appealing thing about Anton is that it can generate 14 microseconds a day of molecular dynamics. And this is in one long trajectory, so it's really quite impressive. But on the surface, you might think, well, actually, you could do that with a GPU cluster. I just mentioned that, we can do about 100 nanoseconds a day. So if we have 140 GPUs, that's 14 microseconds a day as well. And the benefit here is actually it's considerably less expensive than Anton. And this is just buying Anton for less and developing it. And the reason why this is possible is because of OpenMM. But you can imagine that there's a catch here, which is that the Anton's running this where you can have one long trajectory, and the GPU cluster is giving you many shorter trajectories. So in a day, the GPU is giving you 140 100 nanosecond trajectories instead of one 14 microsecond trajectory. And that's where, and so the question is, how can you combine these approaches to do something useful? And so before giving you an introduction to MSMs, I want to give you a sense for why we do what we're doing and why we're doing this way, and maybe even how it compares to other methods. So we have several goals here, and this is something where you may or may not share these goals, but I think these are goals that I think are pretty generic and pretty general. So the first off is that we want to build a model that can predict anything. So we want to predict kinetics, thermodynamics, and structure, not just structure or not just thermodynamics. We want to be able to do everything. Secondly, we want to be able to gain some visualization of what's going on and really come up with trajectories in movies so we can watch what's going on. But then finally, we want to have something that's really reasonably broad applicability, something that's not just useful for protein folding or just useful for GPCRs, but something that we can apply broadly to protein dynamics. And so in that context and those goals, it's useful to compare this to other methods that are available. And so there's many methods that we could talk about. I think I put some of the usual suspects up here. And it's interesting, I think, to think about what are the strengths and weaknesses of these other methods compared to these goals that I've laid out. So if you think about the goals, so one of the first goals is that we want to have something that can really speed up our sampling. And here's something which is, I think is maybe a subtle point that maybe is not well understood, but there are many methods here like metadynamics that use as an input degrees of freedom to sample on. Umbrella sampling is another good example of this. And the challenge here is that while you can sort of sample on those degrees of freedom that you give more rapidly, the degrees of freedom that are orthogonal to that won't be sampled any more rapidly. And so in a sense, if you're sampling, let's say, on RG, like how compact it is, you'll force it to be compact, but you won't necessarily force it to fold or force it to do other things. And so for that reason, I think I would cross off metadynamics as something that doesn't fulfill the goals that we've laid out here. I think metadynamics works very well when you know a priori what are the degrees of freedom that you want to drive it on, and those are the only degrees of freedom you want to drive it on. And I think for low-dimensional systems, especially in quantum mechanics calculations, I think it works quite well. Now, secondly, we often want to discover the endpoints. And so if we want to study protein folding, I don't want to have to assume the final state. If we're studying conformational change, I don't want to have to assume that I'm going to drive it to one point. And this actually comes up even in some cases where recently we were doing a collaboration with an experimentalist lab, and they first gave us a NMR structure for a protein. And then halfway in the collaboration, they said, oh, wait a minute, the NMR structure actually is wrong. It actually should be this other one. And if we were using the string-based methods, we'd be pulling it to that wrong structure. And we'd be able to have simulations to show you, but it probably wouldn't be very useful. And so I would love to have something that doesn't really force you to sort of drive to certain endpoints. And so that tends to take out milestoning or other string or path-based methods. Then finally, I want to be able to predict kinetics in addition to thermodynamics and structure. And so accelerated MD is a very appealing technology, but it's not going to get you kinetics. And so that's why I led off by talking about Anton and MSMs. I think in terms of these goals that I laid out, they're sort of very natural approaches. Okay, so what are our Markov state models with that buildup, and what can they do, and what are they useful for? So the whole idea here is that it's kind of a different way of thinking about doing simulations, and that normally when people do simulations, you run your simulation, then you do your analysis. Here what we're doing is that in a sense we're doing analysis as we run the simulation, and using that analysis to give us some information about the simulation. So what's the analysis that we want to do? Well, we want to parameterize a master equation. And this may or may not be familiar to you, but really all it is that we're asking, how does the probability of being in a state change with some rates? And this is very much similar to like first order chemical kinetics that you've probably seen as an undergraduate, just with lots and lots of states. And the goals are twofold, is that first we can get to these long time scales, and we'll talk about that. But there's a second goal, which I think is actually very important, and maybe sometimes is underlooked, which is that we really want to be able to gain novel insight as well. And so one of the exciting things for me is that now that we've been, and others have been working this for maybe like almost 10 years now, the field has gotten quite rich with many people contributing, and it's actually a pretty exciting time where I think we've been able to do quite a bit in 10 years. Okay, so how does it work? And I think the first question that a lot of people ask that I think is a really kind of counterintuitive thing is that how can having many shorter trajectories, let's say 140 trajectories each at 100 nanoseconds or a few hundred nanoseconds, be as useful as one long trajectory? It's like saying, you know, when I fly to New York City, it takes 6 hours, but that's 6 hours plus or minus an hour. You never fly to New York City in a minute or something like that. And so having lots of flights that go a short amount of time, you'd think wouldn't do anything. And that's because actually the kinetics of chemical dynamics is actually very different than flying around the world. Like flying around the world presumably is roughly Gaussian distributed, whereas chemical kinetics is exponentially distributed. And so what this means is that even for relatively short times, you'll still expect to see something. So if you have just a very simple case of two states and one barrier with a rate constant k, just going a to b, the fraction that will cross from a to b would just be 1 minus e to the minus kt. And at short times, this is approximately equal to just k times t. And so if you do the math, something that is actually kind of cute is that even if k was 1 per microsecond, even if we had 10 nanosecond trajectories, we'd still expect 1% of the trajectories to cross at 10 nanoseconds. Or equivalently, we could have a millisecond process, and we could have 10 microsecond trajectories, and we still expect, you know, a 1 out of 1,000 to cross. And this is how we can run many trajectories, and then we still expect one to cross, even with this type of statistics. So what does that mean in terms of how MSM building looks like? Well, let me give you a simple example. And this is an example that Matt and Robert made up in terms of a simple pedagogical example. And so let's say we're running on this simple 3-well potential. There's these 3 wells. And what MSM running would look like is that we start in one of the wells and we run multiple trajectories. And one of them will just by chance happen to be one of these trajectories that cross. And then at the next stage, what we would do is that we would build a Markov state model. So what this looks like is a decomposition of space into a series of states. And that's what those black lines are. They're sort of chopping up space into a series of states. Then we'd use that model to run more sampling. And the sampling would go in new places and would find new states. And we'd be able to repeat this over and over again until some tolerance of conversions. And the idea here is that now we have a model which is very heavily statistically sampled in all these areas and has really good precision in terms of predicting quantitative properties. But the other key thing about this is unlike methods where you drive on certain degrees of freedom, like umbrella sampling, this is very high dimensional. I've only showed it in 2 dimensions, but you can imagine generalizing this to higher dimensions. This is something where we're driving in all possible dimensions at once. Okay, so that gives you some sense of things. It's maybe more interesting to see this thing in action. What we're doing is we're comparing 2 different sets of simulations with the same amount of aggregate simulation time. On the right, we have one simulation going quickly versus on the left, many going slower. And on the left, we're building MSMs in successive rounds. And one of the first things that you see is that the MSM actually will find a lucky fluctuation and be able to take advantage of it. Whereas in the sort of single long trajectory case, even though it found something that reached some close to some, since it's not building a model, was not able to take advantage of that. So as time goes on, the system continues to search out, and it finds the second minima. You may also notice one thing that's doing is that it's also pushing in directions that on the surface might seem to be not very useful. Like when it's searching over there, you might think, well, there's nothing over there, so why is it searching over there? Well, the thing to keep in mind is that the MSM here has no idea about where the other minima are. So it's just constantly pushing into new directions. And in this case here, it's pushing the directions that found this final minima. And so in this particular example, it finds the minima before the long trajectory even gets out of the first minima. But that's not really the whole game here, because we want to be able to build a model that's statistically significant. So now that it's found this minima, it's continuing to sample it and drive additional sampling in places where we have the least sampling. So anyways, hopefully this gives you some sense of what MSM building would be like. When we've done MSM building in our recent papers, we've done these adaptive sampling rounds largely manually. But even doing a few rounds, let's say 3 or 4 rounds by hand, still has a great improvement over just letting the trajectories go. And in particular, this solves the problem for how MSMs can quickly go find one minima, but after you found the first minima and you want to continue driving, these additional rounds of building MSMs and continuing can be very powerful. So the question is, in the same amount of time, do we have enough statistics? Let's say we have a process that takes tau amount of time to complete. So tau is, let's say, a millisecond or whatever. If you want to run one long trajectory, you might need to sample for 10 tau or 100 tau because you want to watch it go back and forth. For MSMs, typically, the aggregate sampling that we need is on the order of maybe several tau, maybe like 5 tau. And especially with adaptive sampling rounds, I think 5 tau is maybe 10 tau. In that sense, it's in that sense, we get something that's even probably much more precise than what you could get for 10 tau with one long trajectory. And so in that sense, it's much more efficient in addition to being very parallelized. There are methods that claim to be able to converge with time scales less than tau, like 1/10 of a tau or 1/100th of a tau. And in all those cases, it's been my experience that whether explicit or implicitly, they have some degree of freedom that they're driving upon, and that they have some sense of what the answer is. And that may or may not be okay. It may be fine. In my experience, sometimes it's okay, other than there may be orthogonal degrees of freedom that you're missing. And so any method that can do it in less than order tau, in my experience, definitely has something built in. And the basic idea here is this is very easy to parallelize and is quite efficient sampling, whereas just letting it run is obviously going to be more slower and would generate worse statistics with the same amount of data. So the question is, how do you know you've explored all the states? And this is a good question, and it's a challenging one. I think it's an issue for molecular dynamics in general. And so one way to think about this is that when we build our Markov model, we can build a Markov model that corresponds to various timescales. I think we'd be reasonably confident, let's say if we build a Markov model and we can sample millisecond timescales, reasonably confident that if we ran, that if there was some state that had a millisecond rate constant, we would have seen it, or there'd be a pretty high probability we would have seen it. And if something we didn't see, it probably means it has a much longer rate constant. And so if something has a time scale of 1 per second or 1 per day, we're not going to see it. But that's common to all molecular dynamics methods. In a sense, we can very quantitatively say what's the probability of having a state that we didn't see based on the sampling that we did. Yeah. So the question is, how stable is molecular dynamics in general compared to force field? So one of the nice things about this Markov state model formalism is that you can ask that question very directly. And so one way you can ask the question is you can ask, how much would this master equation rate matrix change when you make perturbations? And perturbations to things like a force field. And so what we can show from having this type of formalism is that we can get some sense of what aspects would be the most robust and what would be the least robust. And in general, without going through all the math, the long time scale dynamics are typically the most robust. And the fast dynamics are typically the least robust. But what's interesting about this is that I think this is a property of these types of systems in general, and I think this would be experimentally true as well. So if you're taking a protein that has millisecond conformational change and you're measuring nanosecond properties, I think we can show that that would also be probably not so robust to perturbations in the chemical environment like buffer or pH or mutations. And so the robustness actually goes both ways. Does that answer your question? The other thing that we can do is that, and maybe this might be a more pragmatic approach or a more concrete approach, is that one can run these types of simulations in multiple force fields and compare the results. And this is also one thing that people in my lab and other labs have done, is that we've compared different force fields to different experimental observables. And I think we have a sense that there's a few force fields that reproduce experimental observables well, and there's several that we would also not suggest. Okay, so let's recap where we are. So where we are is that we have this Markov state model, which may have a lot of states, like thousands of states, but it can quantitatively reproduce experiments. We can predict rates and free energies and structure and other things. But one of the things that we'd like to do, I mentioned, is to gain some understanding. And so one last part of Markov state models, which I won't go into too much detail about, but I just want to give you some sense about, is that not only can we, let's say, build a large state model and compare that to experiment, but one thing we can do is we can ask, well, what's the best simpler model that we can sort of gain some insight on? And so instead of building a 3,000 state model, we can build, let's say, a 10 state model. And this, again, is sort of the best 10 state model we can build given the data. But the nice thing about a 10 state model is while it's maybe not as quantitatively predictive as a many state model, it's something where we can gain much more insight in terms of what's going on. And so there's a mathematical process behind this as well. It's called lumping. I won't go into the formalization of lumping, but the cute thing about it is that it's something that I think is on very nice formal ground. So it's not that we're making cartoons or just making stuff up. It's something that can come directly from our model. Okay, so with that, I want to change gears and talk a little bit about what Markov state models can do to give you some sense. And I think Lieping's also talked about this, is that, so first off, MSMs can reach long timescales. And one of the things that I want to show here is that this is a movie not of a single long trajectory in molecular dynamics, but this is a movie made from a Markov state model. So what we do is that we do what's called kinetic Monte Carlo on the transition matrix, or the rate matrix. And essentially what that means is that we pick a state, and then we roll dice to get a random number, and that may lead to transitioning to another state or staying in the same state, depending on the random number and the transition probabilities. If we transition to another state, we pick a structure from another state, and I show that in the movie. If we stay in the same state, I pick another random structure from the same state. And so that's the only process that we're doing here, but it's something where you could quantitatively recapitulate the original dynamics. And I think the hope is that for those of you especially that have looked at MD simulations a lot, I don't think you could look at this and say, oh, this is really different than MD I've seen before. This is something where quantitatively and I think qualitatively with your eyes, you can see something that would reproduce all the aspects of the original MD. And the cute thing is that once you've built your MSM, building these trajectories is trivial. And we can, and so this goes up to 20 microseconds. This movie is quite old. We could easily have made it 20 milliseconds if we wanted to. So one thing I've been personally excited about is that we've come a long way. So if you look at this graph, which is a graph of publications right now from my lab, and soon I'll flip in from other labs, where the x-axis is the year of publication and the y-axis is the time scale for the, in this case, protein folding event. you can see that 10 years ago we were happy to be simulating microsecond processes. And a few years ago, 5 years ago, we got into millisecond timescales and subsequently have been pushing to tens of milliseconds and longer. And the exciting thing for me is that this is on the log scale here. So this is really exponential growth that is really driven by a combination of the fact that MSMs scale really well and GPUs are quite powerful and you can get access to many GPUs. So with that said, while there are a lot of codes that talk about scaling, they typically scale in a much more traditional fashion such that they couldn't get to millisecond timescales or even hundreds of microseconds timescales. And this is a fundamental thing. I think for most other MD codes, getting to a microsecond is a big deal. For us, we'd love to drive this to much longer timescales, and it doesn't require necessarily Folding to do that anymore. You could do that on things like Titan or Blue Waters. And to put this into context, the work that was published from the Shaw lab on this timescale here is typically timescales that are shorter than a millisecond. I think they emphasize that their simulations have millisecond trajectories, but as I mentioned, you have to be able to see it go back and forth many times. So the timescales they simulate typically are tens of microseconds to 100 microseconds tops. And so also one of the things that we and others have been pushing is for MSMs to make quantitative predictions. This is something very simple, just the rate of folding of a protein, but there's other quantitative observables that you can actually pull out of this. And then finally, I want to emphasize some sense of the breadth of things that we could go after. And I'll talk about this in my final talk at the end of tomorrow. But this is work from Morgan Lawrence, and what we're looking at here is two different visualizations of the same trajectory. It's a small molecule binding FKBP, and where the protein flexibility is coming into play because we have this long time scale molecular dynamics. And you can see how the protein flexibility influences how the ligand would bind. And so this is something where we're not building MSMs just for folding anymore, we're building them for many different types of applications. Okay, so to wrap up, I mentioned that we're running this on folding at home. The cloud looks a lot like folding at home, whether you're talking about Amazon EC2 or other resources or even clusters or supercomputers that you have access to. And tomorrow, what I'm going to emphasize is some of the work that we've been doing in pushing into new areas and talk about our work running GPCRs, in this case on Google's cloud infrastructure. And I think with that, I think that's where I intend to leave it. So maybe, hopefully this whets your appetite for stuff to come. I think what I'm going to talk about at the end of tomorrow is sort of the future of MD and where I think all this stuff is going. But for now, I think this might be a good place to stop and take your questions.